All right, let's get right into it. We are talking about a pretty fundamental breakthrough today, one that could literally allow the most powerful AI to run right on your phone. It's a new technology from Google Research called TurboQuant, and it tackles one of the biggest problems holding AI back: its absolutely massive size.
And it really all comes down to this one question. How in the world do you shrink these gigantic AI models, not just a little bit, but by a factor of 6, without sacrificing any of their performance? I mean, it sounds kind of impossible, right? But that is the exact problem TurboQuant was built to solve.
So, here's the game plan for this explainer. We're going to start by digging into AI's huge memory problem. Then we'll look at the classic solution and, well, its flaws. After that, we'll see exactly how TurboQuant's clever two-step trick works. Then we'll get to the good stuff, the real-world results. And finally, we'll talk about what this all means for the future of AI.
Okay, first things first, let's set the stage here. Why is memory such a massive deal in the world of AI anyway?
Well, the simple truth is this. As AI models get smarter and handle longer conversations or bigger documents, their need for memory just explodes. It creates this huge bottleneck that slows everything down and makes running these state-of-the-art models super expensive.
Now, a major reason for this is something called the KV cache, and the analogy here is just perfect. Think of it as the AI's high-speed digital cheat sheet. You know, when you're having a long chat with an AI, it stores all the key points in this cache so it doesn't have to read the entire conversation for every single new word. It's absolutely essential for speed, but you can imagine that cheat sheet gets very, very big very fast.
So how have engineers been dealing with this? Well, the traditional approach is to try and squeeze that data down using a technique called vector quantization.
Vector quantization is basically a data diet for AI. It takes all these super precise numbers the AI works with, like 3.14159, and it rounds them to a much simpler whole number, like 3. It's a way of shrinking the data's footprint while trying your best to keep its essential meaning.
But, and there's always a but, isn't there? This classic solution is not perfect. It comes with a hidden cost that can actually undermine the whole point of compressing the data in the first place.
And that hidden cost is something called memory overhead. See, most of these older methods need to store extra data, kind of like a decoder key, for every single block of information they squeeze down. This adds back 1 or 2 extra bits for every number. And that really adds up, eating away at the savings you were trying to get. It's like going on a diet, but then eating a cookie with every meal.
And this is where TurboQuant enters the scene. It's this incredibly elegant new algorithm that completely gets rid of that wasteful memory overhead. Just gone.
The genius of TurboQuant lies in its really simple 2-step trick. First, it does something clever. It rotates the data. Imagine you have a complex 3D shape. By rotating it just right, you can make it cast a much simpler 2D shadow that's way easier to describe. That's kind of what this does for the data. Then, in step 2, it uses just a tiny bit of its power to double-check and fix any small errors from creating that shadow, making sure the final result is perfectly accurate.
So let's break that down. TurboQuant is really a team of 2 methods working together. On one side, you've got the powerhouse compressor. It does all the heavy lifting, taking up most of the space to shrink the data down. Then on the other side, you have this incredibly precise error checker. It uses just a tiny bit of information to go in and clean up any little mistakes, guaranteeing the final result is unbiased and spot on.
Okay, so that's the theory. But does this thing actually work? Let's take a look at the real-world test results, because honestly, they're pretty mind-blowing.
So the first test is a classic. It's called the needle in a haystack test. You literally hide one tiny, specific piece of information inside a massive document, and then you ask the AI to find it. This is a brutal test of a model's memory and its precision over long contexts.
And the results are just wow. The original full-sized model got a score of 0.997. The model using TurboQuant, with its memory compressed by more than 4 times, also scored 0.997. It's identical. We're talking zero performance loss. It's incredible.
And check this out. This slide really drives the point home. On the long bench benchmark, the original Llama model uses 16 bits for its KV cache and gets a score of 50.06. Now look at TurboQuant. It's using just 3.5 bits, a huge reduction, and it achieves the exact same score, 50.06. No trade-off.
That is a memory compression factor of more than 6 times. That's a game changer. It means the model can handle way longer conversations or just run on much cheaper hardware.
But it's not just about language models. The second major test is in vector search.
Now that's the core technology that powers modern semantic search engines. You know, the kind that understand what you mean, not just the keywords you type.
This chart shows something called recall, which is basically just a measure of how good a search engine is at finding all the relevant results. And as you can see, TurboQuant, those lines at the very top, consistently outperforms the older methods. It's not even close. This means faster, more accurate, and just way more efficient search for all of us.
And speaking of speed, get this. On a top-of-the-line GPU, TurboQuant gives you up to an 8x speedup in one of the most critical parts of how these models think. So it's not just smaller, it's a whole lot faster too.
So let's zoom out for a second. What does all of this really mean? This isn't just a small incremental improvement we're talking about. This is a fundamental leap forward for efficient AI.
So let's tie it all together. Why does this matter to you? Well, it solves a major bottleneck, which lets models like Gemini get even more powerful. It's going to enable the next generation of search. It dramatically cuts the cost of running AI. And maybe most importantly, it paves the way for putting this incredible AI power onto a much wider range of devices. Yeah, maybe even your phone one day.
And you should know, this isn't just some clever engineering hack. The researchers behind it make it very clear that this is a core algorithmic breakthrough. It's all backed up by strong mathematical proofs, which means this thing is robust, it's trustworthy, and it performs about as perfectly as is theoretically possible. It's the real deal.
And all this leaves us with a really fascinating thought to end on. We are seeing AI become dramatically smaller, faster, and more efficient, all without losing its power. So the real question is, as these powerful models are untethered from massive data centers, where are we going to see them pop up next? The possibilities really are just beginning to unfold.